So hello everybody to our webinar today from FLUXANA. Today we want to talk about applications again, and in speciality about making or analyzing sulfides with X-ray fluorescence. Like always in our webinars, you have the possibility to ask questions in the question and answer section or in the chat. And if possible, I can answer them during the webinar, and if not, at the end. And if there are too many, then of course via email later on. And like always, the webinar is recorded so that in the end you will get a copy of it, so that you have the possibility to watch it again. Okay, then thank you for attending, and let's go into our application, sulfides. And why is sulfide interesting? If you have a look here to minerals and ores, you see that there are many elements which are present in nature as sulfides. And sometimes they even look very nice. But of course, mostly we get them as a gray powder into the laboratory. And then we have the challenge to get a result. The idea of doing analysis by X-ray of sulfides is to get at least the main element as precise as possible. And this is also the reason why mostly we use fusion as our sample preparation method, because this gives us the lowest error in preparation and the highest precision in the analysis. To fuse the sample, we need Platinumware. And normally there's an alloy used which consists of 95% platinum and 5% gold, which has a melting point around 1700 degrees. And if you think about the fusion temperature we use is around 1200 degrees. So this is quite in agreement. However, if sulfide is coming into the place and with no pre-treatment, the sulfur would alloy together with the platinum gold and will reduce the melting point of your crucible to something around 1240 degrees, so in the range where we work. And this will then lead, of course, in the destruction of our crucible. Yeah, so this is something we do not like, but which is common for reducing species in samples like sulfide, or others would be metal silica or metal lead, which are even much worse. Yeah. Another point we have to take into account when we do such samples like sulfides with high element concentrations is the so-called memory effect. That means, for example, for copper ores with a very high copper content, let us assume we have a sample with 47% copper, and then I pour it out into my mold and I prepare the next sample, and let us assume the next sample is free of copper, then still I would measure something around 0.3%. Why? Because the copper is going into the platinum, and in the next fusion it's bleeding out, and this contaminates our next sample. So there you have to be careful. That means you need to do a kind of a cleaning fusion just with flux, or with another sample which is free of copper, so that the copper then is reduced in the platinum, or you have an own set of Platinumware only for this kind of application. Yeah. But very often you can see when you make a blank afterwards that even the blank is still blue, and so you see the copper by your eyes. You don't need an X-ray instrument. For example, or for comparison, if we look at cobalt, there it's a bit different. Same concentration range, but only a small contamination we see into the next speed. So copper is really the most serious case. The other elements like iron, nickel, zinc, they also show this, but on a very low level. But be careful when you have high concentration elements, and you have to see some cross-contamination there. To avoid this destruction of the Platinumware, we need to oxidize our sulfidic sample. And what we could use there are any kind of nitrates. Yeah? So like shown in this reaction, the sulfide is then converted into sulfate, and sulfate is then inert to platinum. There's no reaction anymore. And but not all sulfur or not all sulfide is always converted into sulfate. There's also the possibility that there's volatile sulfur formed. And this is a bit the problem, that the quantification of sulfur in such sulfidic ores is mostly difficult, because we lose some sulfur in that process. And that's why sulfur is mostly taken out of that type of analysis by X-ray, because it's not really quantitative. You see that there is a big choice of different nitrates you could use. It depends a little bit on what elements you can spare out, because it's in the oxidizer. What we use normally is sodium nitrate or strontium nitrate. Both are very easy to handle, not hygroscopic, and therefore in the real world good to handle. While lithium nitrate, for example, is very hygroscopic, not easy to use, and therefore we prefer the other two. But let's talk about flux. What kind of flux can we use to do fusions? I put you here the phase diagram of boron oxide and lithium oxide, the two basic components to form lithium borate. And how do we read this phase diagram? You have here the concentration level of boron oxide. So here we have 100%, and we have 0% lithium oxide at this point. If we go to the middle at 50, we have 50% lithium oxide and 50% boron oxide. The curve here is the melting temperature. So that means that with different composition between the two, we have a different melting point. And there are some extreme points, like the highest one. This is exactly the point of lithium tetraborate, so the Le2B407. And then you see here the lowest point at a range of something 50-50 between the two. And for our fusion, we just use the lithium borates, and then it's only that region, which is interesting. That means we have either lithium metaborate, which is here, or lithium tetraborate, which is here. And if I zoom in a little bit, you see here again the lithium metaborate with a melting point from 850 degrees and tetraborate with 917. Then we have here an eutectic mixture, which is 34% lithium tetraborate and 66 meta, or we call it sometimes 1.2 molar to 2.2 molar. And this is then the lowest melting point we can achieve in lithium borates with 832 degrees. And the other mixtures, like the 6634 tetraborate, metaborate, is around here, and 50-50 would be around here. So you see, this is our playground with the lithium borates we can use for fusion, for XRF. And so one big difference is the melting point, but the other big difference we have to take into account is the glass forming. While boron oxide, which is way down here, really forms a good glass. This is also the case for lithium tetraborate, but then it's decreasing until lithium metaborate is not given a glass. The crystallization speed is really too quick, so that we are not able to get a glass out of it. And this is now a bit our challenge, that going in that direction, which means increasing the metaborate part, the ability to form a glass is decreasing continuously. So that's why it's sometimes difficult to use with such a flux to get immediately a glass. So you need a lot of optimization of your recipe until it works. I give you some examples. For example, here we have this this flux 1.2, 2.2. So this at this point, and we have here a recipe of a lead concentrate. So let's get back to sulfides, and in a ratio of 0.8 gram sample to 7 gram lead concentrate, 1.2 gram sodium nitrate as oxidizer, and as non-wetting agent we use ammonium iodide. And first trials, you see a bit of crystallization, cracking. But if we would do exactly the same recipe in a 6634, So this kind of flux here, much better glass forming, we get a nice glass. So you see already the challenge between the two. Second example, same recipe, but higher dilution. You can see it in the color, how it gets lighter. It's already getting better, the glass. Crystallization in these parts has disappeared, but still cracking not yet perfect. So this would need some more optimization. This recipe with that flux just working. So you see the band where this is giving a good glass is very narrow, while here this is a much better flexible flux. You can use it with more recipes. Other thing we have to discuss is the non-wetting agent. Also here a sulfide example. Now it's copper sulfide. Recipe 0.5 gram sample, 7 gram. Again, this 1.2, 2.2 flux, and 1 gram sodium nitrate as oxidizer. And here we have 3 different non-wetting agents. Ammonium iodide liquid, let me say in a 25% solution. Then ammonium iodide solid, or lithium bromide solid. And also you see here in that order, it's getting better and better, and in the end giving a glass. Why? The iodide as a non-wetting agent is very volatile, so you lose a lot during the fusion. You lose more when it's liquid than it's solid, and of course bromide is not as volatile, so in this case it remains better in the bead, in the melt, and this is why this gives the glass, while this still needs more non-wetting agents or a different flux, so it needs more optimization. So you see the way where you can go to optimize your recipe in a way that in the end you get what you want. So this is the real application development work. Okay, now let's talk about the method itself. How do we do sulfides? So there are 2 methods. One method is we take our sample and we take the oxidizer, the nitrate, mix it, put it in a crucible, and at 600 to 800 degrees we roast it. We oxidize it in the muffle furnace. We take it out, cool it down, and then we add our lithium borate, and then we do the fusion. One possibility. Second possibility is we take the lithium borate already in our crucible. We mix sample and oxidizer together, put it on top. Again, we do just our roasting in the muffle furnace and take it out. And then again, we take it into a fusion machine and fuse it at the high temperature. Method 1 makes some trouble because very often it overreacts. So that, like you see here, the whole crucible is now spilled with sample oxidizer mixture, and it even went outside. So this is a bit difficult to get under control. This is why over time we skipped that method and we just use this method as the real stable method in the daily work. In the real world, this would work like this, that we take our flux, we would add an internal standard. Why we do that, I will explain a bit later. Then we take our sample and the oxidizer in one little dish, and we pour the flux and the internal standard in the crucible, mix it, and then add on top this oxidizer sample mixture. Just place on top. Then we put it in our rack or in a muffle furnace and oxidize it. Like I said, around 600 to 800 degrees. And when it comes out, you see the flux is nearly untouched because temperature was too low, no contact with the platinumware, so you are safe. And the sample is really oxidized and on top. And now it's time to put it into a fusion machine to cast the glass in the end. When it comes back, we will have our empty crucibles, which because of the non-wetting agents, they are practically empty. And if we take them away, you see the glass, in this case, 2 copper ores and 2 zinc ores, nicely formed with a good recipe. Talking about calibration, for a first start, we took samples or standard materials from EMIS, OREAS, NIST, NCS, CanMet, and what was missing, we just made our own from pure chemicals. And so that in the end, we have a nice coverage for high iron, for high copper, then for high cobalt, some arsenic, here high lead, high zinc, and of course the other elements which are as side components in these materials. Also silver, you can see here. So this gives quite a nice arrangement of calibration curves. And now let's also have a word to the internal standard. Why are we using this? Mostly the idea is to use the Platinumware as long as possible. And when you look on these lines we use for determining the main components in that application, so we have the lead L-alpha line, or we have the zinc K-alpha, copper and nickel K-alpha, and tungsten is just in between, so it's a neighbor element. And if we now would form the ratio between the analytical line and the internal standard line, then we see that all effects like bit consuming of the Platinumware, the dish, both intensity will be affected in the same way. That means the ratio here is just the same. Yeah. So in this way, we can get our whole routine results a bit more stable, but of course we have some additional work in weighing. So this is a bit of balance. What is less work? Do we exchange the platinum earlier, or do we just go en masse and say, hey, I need throughput and I need to do many samples in a day? Then this internal standard really pays back. Okay, let's see some calibration curves, like for example here for lead. So you see we have here two groups, a high range and a low range. All together would be around 0.42% standard deviation. Of course, in the end, what I would do is, when we go then in the routine analysis, to take this general application and split it into a lead ore, into a copper ore, cobalt ore calibration. So then you can make fine adjustment, split the calibration ranges so that you get even more precise and accurate in these ranges. Yeah. This, for example, you can see in copper. There we have two groups here on calibration. Altogether has quite a high standard deviation. But for example, if we just take the low side, we are already at 0.15%, and this is what you want in the end. Some results. So if we just prepare from a copper ore two classes from the same ore, you see a fantastic precision. So the reproducibility of the two preparation is really perfect. Same we could say for the lead ore, or the same we could say for the cobalt ore. Yeah. So you see that for the sulfur, like I told you already, there's some risk always that you lose it. Here you will see a higher error, but for the element of interest, the main component, and of course also the side components, even the silver here, you can really do a good accurate analytic here. Another example is a control sample from a copper sulfide you can buy from EMIS. And this copper sample has a range of 15% roughly. And in the round robin study, they had a variation of plus minus 1%, we can say. This is the blue range. And when we just make a fusion control sample, you see here beginning of March until mid of May, then you see that the fusion preparation here is really doing good and fits very well into this application, and especially for the control sample. Okay, let's summarize the whole application. So what we need is an oxidizer so that the sulfide is converted into sulfate, and there is no risk that the Platinumware is attacked. We have to make sure that the temperature for the oxidation is low enough. We use that two-step procedure so that we have no risk to destroy the platinum. We use the internal standard to have a longer use of the Platinumware. Then, of course, we need a selection of CRMs, and we need a reproducible fusion process. And of course, cleaning of Platinumware with memory effects also has to be taken into account. And now I wanted to show you a little bit how we do that in our laboratory. So we use that Vitriox 4+, which has 4 samples at a time in the furnace, but it can load up to 16. Yeah? So you see, you can even define 4 different applications with different timing and temperatures, and then the machine automatically handles the 4 racks. And you see there's a storage then where the 4 are loaded into, and then one after the next is taken by the autosampler and is then just put into the furnace. The furnace has the door as a bottom to keep it as hot as possible when you open the door, and the design is round so that we can turn it around. It's turning all the time to distribute the heat continuously. You know it from your microwave at home. And for agitation, we do it at high speed. When this is finished, about 15 to 20 minutes, then the autosampler comes back and just takes it, pours it, and then puts it into the cooling station. And then already the next could be introduced so that you save during the cooling at that time already to do the next one. Yeah, you see here, this is going into the cooling directly after it took it from the furnace. And when it's cold, you can take it out. And of course, also you could combine it with a cobot so that you even can load not 16 samples, for example, you can load then 32 or 64 samples fully automatically. Yeah? So in this way, you get a high degree of automation of your machine. Okay, that's it for the moment. I would like to just also announce you the next webinar, which is in July. And now I'm looking for any questions which are here in my chat. There is a question: what would be your advice for analyzing low concentration around 400 ppm fluorine, sulfur, and chlorine in furnace bottom ash of polymer waste? So these are all 3 volatile elements and at very low level. So I would say they will be lost during a fusion process. So that's why the only chance is that you try it by press pellet. Press pellet is important because they are all measured at the surface. Fluorine 400 ppm is a challenge. Sulfur and chlorine wouldn't be a problem. Yeah, I think this would be probably the way to do it. Any more questions? Perhaps while there are some more questions coming, this procedure with the 2 steps oxidization, you could also use for other applications, for example, for metal powders or for any kind of ferroalloys. It could be used also for some kind of silicon carbide. Yeah, so these all kind of reduced species where there is a risk to damage your Platinumware and where you would like to have a safe procedure. Yeah, so always there we use this kind of 2-step procedure. Okay, there are no more questions. So I think I'm quite in time then. And if you like to ask something, you have my email over the info@fluxana.de. You could always send in any kind of questions. I thank you very much for your attention today. And like I told you, you get a copy of this presentation later on. And I thank you very much and hope to see you soon in the next webinar. Thank you very much. Bye-bye.